So in this video I want to give you some practice and feedback on sketching vector fields. So we're going to be looking at vector fields in 2 dimensions, unit vectors I and j. So we've got the x direction, unit vector I, the y direction, unit vector j. And I'm just going to draw one example on this side, and then afterwards I will give you some questions and I suggest you have a look at them, try to do them yourselves, and then I will give you the answers. So here is our example. We have a vector field, depends on x and y, and it's equal to r, where r is the position vector. In other words, it is xi plus yj, I and j being the unit vectors in the x and y directions. So the magnitude of f is the magnitude of r vector, and that we write as r without the vector, and it is easily worked out to be the square root of this coefficient squared plus this coefficient squared. So it's the square root of x squared plus y squared, and from polar coordinates you know that the square root of x squared plus y squared is r. So what do we see from this? Well, first of all, two things. First of all, our vector, the vector field vector, always points away from the origin because it points in the direction of the position vector. So if we were here, say, it would be pointing in that direction because that is the direction of the position vector to that point. Also, the magnitude of the vector is equal to r, and r is the distance of the point from the origin. So if we've got 2 points that lie on a circle of a given radius, that radius would be r, then the magnitude of the vector is the same at both of those points, or indeed any point on a given circle centered at the origin, and that means that those vectors, although they're pointing in different directions, they're all pointing away from the origin, they will all have the same size. So let me just draw for you a circle. I'm going to draw this very faintly because I don't want it to really distract us too much. We don't need to draw these things normally, but this is just to give us some practice. So if I draw a circle here, then all of the vectors of the points on that circle will have the same length. So if I draw that one there with this length here, I should now try to draw all the other vectors on the circle as having the same length, but pointing in every case away from the origin. And your artistic talent, or lack of it in my case, are going to be the only limiting features. So this is what would happen. If you were to look at a circle that was closer to the origin, you would have shorter arrows, and the ratio of the length of the arrows would be equal to the ratio of the distances that these circles are from the origin. So this looks to me as though it's about 1/3 of the radius of that circle, so these arrows here should be about 1/3 of that length. So I'm just going to draw some very short arrows here, and I'm not going to draw as many because I'm not going to fit them in. Okay, if we go out to a larger circle, I'm not going to draw the circle anymore, but I'm going to assume that I can just try to work out what it would roughly be like. I have larger arrows. And this is the sort of thing that computer software will draw for us. It's something like that. But you can start to see why it's doing what it's doing. Then up here. So again, all of these arrows are supposed to have the same length, and you can see we're going from shorter to longer again arrows as we go away from the origin. And all of these arrows, if you trace them back, as far as I've drawn them correctly, should be pointing straight back at the origin. So this is a vector field, and this is the vector field for F is equal to R. So on the next slide, I'm going to write down some vector fields, ask you to have a go, and then afterwards I will give you some rough sketches of what they should look like. So here I've drawn or written for you 4 vector fields. R has exactly the same meaning, it's the position vector as before, and what I would encourage you to do is to try and draw them with pen and paper, and then on the next few slides I have talked about what their solutions are, what they look like, and I have tried to draw them on the relevant slides. So we've got 4 more slides to come, but before you look at them, try them please with pen and paper. I think that way you'll get much more out of this video. See you in a few minutes. Okay, welcome back. Let's look at the first one on the next slide. So for this example, our vector field is y times the unit vector j. And the unit vector j points in this direction, straight upwards. So at all points, all x and y, our unit vector you might think is going to point up, but bear in mind if y is negative, that reverses the direction of the vector. So if y is negative, in other words, we're below the x-axis, it will point straight downwards. So we already know a great deal. In the upper half plane, it points upwards at all points. In the lower half plane, it points downwards at all points. We need to look at the magnitude of our vector field. That's very easy. It's just going to be the square root of y squared, and that's the modulus of y. So the magnitude is just dependent upon what the value of y is, and it's independent of x. So that means, if we think about it, that for a given line, let me just draw a line here with the help of the laser pointer. So I'm drawing a line here parallel to the x-axis and above. Along this line, the arrows will have exactly the same size and they will all point upwards. If I take a line the same distance below the x-axis, so I draw it here at the same distance below as the line was above, I will have arrows with the same size but pointing straight downwards. So let me just try to draw that. So with the help of a laser pointer, if I draw a line here parallel to the x-axis, at all points along that line, the arrows are going to point upwards, the vectors pointing upwards, and it has the same magnitude. If I go the same distance below the x-axis, then at all of the points on this line, the vector has the same magnitude, so the arrows we draw will have the same length, but they will be pointing downwards, so all pointing downwards. So let me just try to draw some arrows to transmit this information to someone seeing the sketch. So I'm going to draw it here. I'm starting to think maybe I've drawn them a little bit too close together, but hey, I've started, so I'll finish, as they say. And then down here at the same distance below, and I'm trying to draw it very symmetrically, we have vectors of the same magnitude as we go along the line, same magnitude as these, but an opposite direction. Now, if we go further up, the magnitude increases as the modulus does, so it increases linearly with the distance. So if I go twice as far away, I'm going to have vectors that are twice as long. So let me just try to draw some of those. So I'm going to try and draw this one. Let me draw slightly fewer perhaps, just to fit them in. These are all supposed to have the same length, but they are longer. And clearly you can see were you to go further down and draw an arrow here, it would be even longer again. And this is the vector field F is equal to yj. So with that, let's move on to the next exercise. So our second example here is R, the position vector, divided by the square of its magnitude. And the fact that we have the position vector here, which is giving us the direction, this is just telling us a scalar that's multiplying it, tells us that our vector is radial. It's always pointing away from the origin. So if you are here, you're pointing that way, straight away from the origin. If you're here, you'd be pointing along the negative x-axis. However, this is not the same as the initial problem we looked at because of this factor of 1 over r squared multiplying the position vector. And in particular, that's going to change the magnitude of our vector field. So to work out the magnitude of the vector field, we work out the magnitude of the position vector, but that is just r, because you take the x, you square it, the y, you square it, you add them together, x squared plus y squared, and take the square root. And the square root of x squared plus y squared is equal to r, the magnitude of the position vector. On the bottom, we have r squared, or x squared plus y squared, and if you have a number multiplying a vector, and this is a scalar, so the scalar multiplying the vector, it just multiplies the magnitude. So this factor of r squared just sits there for the magnitude. In principle, you can square it, get r to the fourth, take the square root, get back to r squared, but it just sits there. So the magnitude of this vector field is the magnitude of the numerator, r, divided by r squared, and the r squared are going to partly cancel, and we're going to be left with 1 over r. And this means that the magnitude is 1 over r, it goes as the distance, 1 over the distance from the origin, and it also tells us if x is equal to y is equal to 0, in other words, if we're at the origin, x is y is equal to 0, you would have here 1 divided by 0, your vector field would have a diverging magnitude, so that's not in the domain of the vector field. Our vector field is not defined at the origin. Now, as you go close to the origin, the arrows are going to be all pointing away from the origin, but they're going to be extremely long. And as you go further away, on any given circle, the vector field has the same magnitude for that particular circle and is always pointing straight away from the origin. So let me just try to draw a couple of circles here. So if I say that here it looks like this, I'm trying to draw these things roughly on a circle, and I'm trying to draw them with roughly the same distance. I think this one actually I've drawn a little bit too far away. I'll get rid of it, and having got rid of it, I will redraw it a little bit closer to the origin. I'm trying to draw it on a circle, so it's something like here. Okay. And if I come in closer, say down to here, I'm going to have arrows as well, but they're going to be significantly longer. So let me just try to draw some of those in. Like this. And if I were to go further out again, I would draw another set of even smaller arrows, shorter arrows, again pointing away from the origin. So that is roughly what our vector field, r, the position vector, divided by the square of its magnitude, looks like. And what we're trying to see here is, again, the direction. These are radial arrows in all cases, but the magnitude tells us how long they should be, and we're seeing that because they go as 1 over r, they get smaller as you go further away and longer as you come closer to the origin. With that, we'll move on to the next example. So for this example, we have a vector field which is y times I, the unit vector in the I direction, minus y times j, the unit vector in the j direction. Y we see is a common factor, so why don't we write this as y times I minus j. And I minus j is a fixed vector, so it's a fixed direction, pointing in the I direction minus a vector in the j direction of the same length, so it's pointing downwards at 45 degrees in this direction. So from the origin, this angle is 45 degrees, or pi over 4. So that is the direction it's pointing in, you would say. But again, y, if we are below the x-axis, is negative. So if you're below the x-axis, that means it's not pointing in this direction. It would be pointing in the opposite, the reverse direction. So it would be pointing from here, say, upwards and to the left. Whereas here, it's pointing downwards and to the right. Okay, the magnitude of this vector field is the square root of the square of this coefficient plus the square of this coefficient minus y squared. Y squared plus minus y squared is 2y squared. So the magnitude, the square root of it, is the square root of 2 times the square root of y squared, which is the modulus of y. So that means if you're at a certain distance above the x-axis or the same distance below the x-axis, there is a symmetry. The lines, the arrows that tell you how big the vector field is are going to have the same length, but they're going to have reversed directions. So here, that way, here, that way. Okay, so that tells us everything, and we can just draw some vector fields. So let's start at, say, here above the x-axis, and let's say that this is our vector. I'm trying to draw them all in the same direction. I'm trying to draw them all at 45 degrees. And if we go to the equivalent points below the x-axis, then by symmetry, we are going to have vector fields. It should be the same length, and it should just be the reversed direction. Okay, if we go further up, if we go, say, twice as far up, that means we have doubled the value of y. And if we double the value of y, we are going to double the magnitude of our vector field. And that means that we are going to draw lines that are twice as long. So if I go to here, say, I want to draw something which is twice as long. I'll draw somewhat fewer of them. Go back to here, and to here. And again, we have this symmetry. And if we were to go down to here, say, we would draw lines that are even longer. So let me just draw a few up here. I've got a bit more room here. I'll draw a line here, say, an arrow here. These are all supposed to be parallel to each other. Any failure is my lack of artistic ability. And these lines here are, I hope I'm drawing them clearly, longer than the lines above. And that is our vector field, h of x and y, which is yi minus yj. So with that, let's move on to the next example. So in our final example, here is our vector field. It's y times I, the unit vector in the I direction, minus x times j, the unit vector in the j direction. And the magnitude of this vector field is found by squaring that and then adding the square of this. So it's y squared plus minus x squared, so that's the same as y squared plus x squared. I'm just writing it here in the more conventional ordering. And x squared plus y squared is r squared, and the square root of r squared is r. We don't need to write the modulus of r because r means the distance of the point or from the origin. So it's always, by definition, positive. So we see that the length of the vector field, the length of these representative arrows that we're going to draw, only depends upon the distance from the origin. So again here, if you draw a circle, as you go around the circle, for any point on it, you're going to draw the same length of arrow. The only thing that's going to change is the direction. So let's start to think about what that direction might be. Well, first of all, we see that if we are on the x-axis, that means that y is 0, and it tells us that the vector field for any point on the x-axis is minus x times j. So that means if x is positive, we have something negative overall times j, so it's pointing downwards. If x is negative, minus a negative quantity is positive, you have something positive times j, it is pointing upwards. So we have something pointing down, pointing up. And as you go further away, it's pointing down still, but it's bigger. As you go further away, it's pointing up still, but it's bigger. But let's just try and look at a circle first. So here I'm going to draw a vector which is pointing straight down. And at a supposedly identical distance, on this side we have a vector of what's supposed to be the same length pointing upwards. We now go to a point on the y-axis, and if we're on the y-axis, x is 0, so this vanishes, and we have y times the unit vector in the I direction If y is positive, if we're above the x-axis, we have something positive times I, it is pointing this way, to the right. If y is negative, we have minus something times I, so it is pointing this way to the left. And the magnitude, if we're at the same distance from the origin that we were at this point, the magnitude of this vector should be the same as the magnitude of this vector. And then we go down here to the same distance below, and we have the same thing here. What about if we were here, say, at the same distance, so staying on this circle? So if you're at this position here, x is positive, y is positive, and if we've gone to 45 degrees, x and y have the same value. So x and y, if they have the same value, could be taken out, and you have the value of x and y times I minus j. So it would be pointing straight downwards at 45 degrees. So at such a point, we would have an arrow pointing straight downwards. And I think you can start to see how this is going to work. As you go around this circle, our vector is tangential to the circle. So we have something like that, like that, like that. And now if we go further out, if we increase the radius, all we're going to do is get exactly the same thing, but the radius has become larger, so the length of these vectors is going to become larger with it. If you double the radius, you double the length of the vectors. So let's say we've gone to here, this is roughly double the distance, roughly, and I'm going to roughly double the length of the vectors. I think it's easiest to draw the ones on the axes first. Something like that, something like this, something like this. And then again here, and again here. So these points, the base points, are supposed to be here at 45 degrees from the x and y axes. So this again should be at the same angle here. This should be at the same angle here. They're not going to be drawn perfectly because I can't draw it perfectly by hand. But I hope this is giving you the idea what happens. You could draw a third circle should you wish, and computer algebra will draw these things for you with more arrows than you yourself are going to be comfortable drawing by hand. So here, labeling the figure is our vector field yi minus xj, and the vector. So what we've tried to do in this set of examples is to draw vector fields representing them through a set of arrows at some chosen points. Computer algebra will draw more points than we can draw, but we can choose some points, draw some arrows to represent the size and direction of the vector field at a set of points, and try to transmit information about what the vector field looks like. So I think here, for example, we can see some sort of rotation. We have an idea that this could be describing a vortex. But with that, I will stop this video.